Hi there, warriors. This is Miss Lemons, and today we are going to be talking about thermochemical equations. All right, so thermochemical equations. Every chemical reaction obeys two fundamental laws: the law of conservation of mass and the law of conservation of energy. So remember that the law of conservation of mass tells us that matter cannot be created or destroyed, it has to be rearranged. And the law of conservation of energy tells us that energy cannot be created or destroyed, it's just transferred from one item to another. Okay, so in reactions, the energy that's absorbed, or a positive Q, I don't know why that got cut off, but that's positive Q, or released negative Q value, is often thermal energy. And remember, thermal energy is heat energy, and it's the energy that's associated with the random motion of atoms and molecules, or that kinetic energy. Remember, temperature is the measure, the average kinetic energy of particles in a substance, and heat energy happens when there's a differential in temperature, a difference in temperature between two objects. So thermal energy, or heat energy, is the energy that's associated with kinetic energy. Temperature measures that kinetic energy, okay? It's a little bit of review at this point. Okay, so thermochemical equations, like what are they? So they are just chemical equations like we've seen throughout the school year, but this time they include the change of heat content, okay? And we denote the change in heat content as delta capital H, delta H. And you're gonna see this pretty much for the rest of the unit, this variable. We can incorporate the change of heat content either by placing it as a reactant or a product in the chemical equation, or we can list it next to the chemical equation. So this heat content that I keep talking about, this delta H, this is called enthalpy. So a little bit about what a thermochemical equation looks like. Remember when I said that those are chemical equations that incorporate heat as a product or a reactant? So you can see down here, this right here is a chemical equation, and we've added heat content. You can tell that's heat because it's kilojoules, and we know that's how we measure heat, right? Kilojoules. So we put it as a reactant in this equation. So it's just like any other ingredient in a recipe. When we write a thermochemical equation now, we're adding heat as one of those ingredients in our chemical reaction. I also said that you can list the heat content next to the chemical reaction. So here we just had a typical chemical reaction, the same one from above, but this time, instead of incorporating it into the chemical equation, we can list it off to the side with a sign telling us if this is being absorbed or used as a reactant, or is it being released as a product. Okay, so in this case, it's being absorbed, right? We're gaining heat energy, so it's being put into the system. And then, of course, I just gave you guys the regular chemical equation without heat content. This is a chemical equation. These are thermochemical equations because we've included the thermal energy, that heat content. Okay, so let's talk a little bit more about what enthalpy is. This is a quite long list, but hopefully you guys understand where I'm going with here. So enthalpy describes the flow of heat in a system. It is measured in units of kilojoules or kilojoules per mole, depending on what you're doing with that value. Now, guys, I've mentioned this before, but knowing your units and your variables for thermochemistry is so important, okay? Please make sure you know that capital H is enthalpy, and it's measured in kilojoules or kilojoules per mole. If you're getting a little rusty on those units, make sure you take a look at the Quizlet that I posted on the webpage. Enthalpy cannot be measured by itself. We can't measure H. It doesn't work that way. But we can measure a change in enthalpy. So we can't measure H, but we can measure delta H, the change in enthalpy. Okay, so delta H is that change in enthalpy, just like delta T is change in temperature. So delta H represents the heat energy that changes in a chemical reaction. And then delta heat naught, or delta H naught, that little zero is naught, that is the energy changes that have been measured at standard conditions. And we're going to talk a little bit more about what it means to be at standard conditions. But when you see that little naught symbol, the little 0 up above there, that means we're at standard conditions, which just means that the reaction took place at 25 degrees Celsius in 1 atmosphere of pressure. Okay, so the connection to our calorimetry lab. Okay, why are we talking about enthalpy? This seems like such a jump from, learning about Q equals MCAT and then using a coffee cup calorimeter yesterday. And now, why are we talking about this? Well, in our calorimetry lab, we were measuring the change in heat energy, or Q, of a system, right? We were looking at a hot piece of metal, placing it into the cool water, seeing how much heat energy was released to the surroundings, the water. Well, we also happened to be measuring the change in enthalpy while we were doing calorimetry. This means that Q is equal to delta H, which is awesome. And just so you know, Q equals delta H under conditions of constant pressure and temperature, but we are always going to have these conditions in this class, so we just assume that Q is always equal to delta H. So if delta H is equal to Q, that means that in exothermic reactions, heat energy is released with a negative Q. And that also means that the system will decrease in temperature, which gives us a negative delta T. And so we would say that the enthalpy change is negative also. So we would say negative delta H. This means that energy is produced. So it's a product, right? It's being released. It's a result of a chemical reaction. In endothermic reactions, heat energy is absorbed, and the system will increase that temperature. So we have a positive delta T, and we have a positive Q. So we would say that the enthalpy change is also positive. That's a positive delta H. So do you see how all of these are mathematically related? They are all directly proportional, right? If we have a positive Q, we have a positive delta T, we'll have a positive delta H. And because it's being absorbed, that means that energy is consumed. So we consider energy to be a reactant. So when we're writing our thermochemical equations, we want to be thinking about how heat is related as a product or a reactant. If it's an exothermic reaction, it is a product. It's produced as a result of the reaction. If it's an endothermic reaction, it's absorbed, it's required, it's one of the ingredients you need to perform that chemical reaction. Okay, so let's take a look at thermochemical equations with exothermic reactions. So remember, exothermic reactions release energy. The formation of water is an exothermic reaction. So we would actually write it like this. So that's H2 plus O2 yields 2H2O plus 571.5 kilojoules. So what this equation tells me is that if I have 2 moles of H2 and 1 mole of O2, I'm going to produce not only 2 moles of water, but also 571.5 kilojoules of heat energy. So I'm producing heat, right? It's being released from the system, so it should feel warm, right? We should feel heat coming off the system. Another way that we can write this would be with the heat term on the side. Now, I personally like to write it this way, and here is why. I want you guys to notice the difference in values here. The value of the number is actually the same, right? That has not changed. But the biggest difference is this negative sign. And we have learned that having a negative or a positive symbol in thermochemistry is really important to pay attention to because it tells you the direction of heat energy. Is it going into the system or out of the system? Is it entering or exiting, right? So in this case, because this is exothermic, it's releasing energy. We know that we want our delta. We know that our Q value would be negative. And if we have a negative Q value, then we should have a negative delta T. And if we have a negative delta T, we should also have a negative delta H. Now, notice that I didn't put the negative number here. Why? Well, I didn't need to put the negative number here because remember, the negative tells us that this is heat exiting the system. It's exothermic. We can see that with the negative symbol. But if I incorporate heat into the thermochemical equation, we can see that heat is a product. It's exiting the system. It is happening as a result of these two reactants coming together, okay? So if you write it off to the side, that's awesome, but make sure you include that symbol. It's the same reaction, and there's two different ways to write it. So let's take a look at this for the endothermic reaction. Remember, endothermic reactions absorb energy, okay? So the decomposition of water is an endothermic reaction. We could write it like this, and honestly, folks, I know a lot of people ask me, like, does it matter if I put the number first or the water first? It doesn't matter, right? Addition, 2 plus 3 is 5, 3 plus 2 is still 5. So it doesn't matter what order you put it in. So here you can see that we've incorporated the heat content into the actual chemical equation, which is totally fine. We included the unit, kilojoule, and this tells us that in order for us to decompose water, we need to implement 571.5 kilojoules for every 2 moles of water, right? Well, what if I had 4 moles of water? Well, then you would have to double the amount of energy you put in the system if you want to decompose all 4 moles of water. Well, what if I had 100 times more water? Well, then you would need to have 100 times more energy in order to fully decompose all of that water, right? So our heat content is it's entering the system, it's entering the chemical equation, therefore this is an endothermic reaction. We could write this the second way, which is having the heat content off to the side, and notice that I do intentionally put a positive symbol in front of 571.5. I also now want to point out here that the units are slightly different. It says kilojoules per mole. So when we're inside the actual equation, you don't need to say kilojoules per mole because this right here is already telling us the ratio per mole. For every mole of oxygen, I need 2 moles. I'll produce 2 moles of hydrogen. I'll start with 2 moles of H2O, and I'll need this many kilojoules for this entire reaction. But the reason why we have to write kilojoules per mole is because it's no longer a part of the chemical equation. So we have to say, okay, for this reaction, if we perform this reaction 1 time, for every 1 reaction, we need 571.5 kilojoules per mole of the reaction, okay? Again, same reaction, 2 different ways to write it. You can choose which way you want to do. I personally prefer the second method just because it's easier to balance out chemical equations without the numbers in it, and I keep track of my signs. Remember, having a positive or negative is really important to keep